Hey guys, our very first number theory proof, and in this video we're gonna prove that the square root of 2 is an irrational number. That is, we're gonna show that the square root of 2 is not a rational number. It's irrational. It's crazy. Yeah, we're gonna do what's called a proof by contradiction, or an indirect proof. So we have to start by assuming the opposite of what we're trying to show. So assume that the square root of 2 is rational. Notice that this assumption is exactly the opposite of what we're trying to show. What we're trying to show is that the square root of 2 is not rational, right? Okay, and then we're gonna, through a sequence of reasoning, show that this assumption here is gonna lead to a faulty conclusion or a contradiction, and therefore this assumption must be false, and that its opposite, the original statement, must be true. That's the plan. Okay, now, if the square root of 2 is rational, then it must mean that we can write square root of 2 as p divided by q for two integers p and q. So p and q, members of the integers. That's all that like last pair of symbols here mean. This means inside of the integers. So p and q are inside of the integers, the set of integers. And we also need a very important addition, which is that p and q have a greatest common divisor of 1. GCD PQ, the greatest common divisor of p and q is 1. That is, this is in most reduced form. This is true of every rational number. Every rational number, like 2/3, can be written as one integer divided by another integer in most reduced form. In other words, like 4/6 will then be reduced to this rational number, but every rational number can be written in this way. One integer divided by another integer, where those two integers have a greatest common divisor of 1. All right? Okay, very important. Now, so since we're saying that square root of 2 is rational, then this must follow with all of this stuff, right? Okay, cool. But then saying that square root of 2 equals the quotient of two integers, so p divided by q, will allow us to write the following upon squaring both sides of this equation. If we square the left side and the right side, then we can write that 2 is equal to p squared divided by q squared. But then this in turn implies that p squared is equal to 2 times q squared. Now, we said that q was a member of the integers. So q squared is a member of the integers. And we have that p squared is equal to 2 times an integer. So that means that p squared is even. P squared is even, because all even numbers can be written as 2 times an integer, right? Okay, cool. But if p squared is even, that means that p is even. And that's because p was either even or odd to start with. And if we do odd times odd for p squared, right, if we assume that p was odd, and we did odd times odd, then we'd get an odd number. But p squared is even. Therefore, p must have been even, because that's the only way we can get p squared to be even, right? Okay, cool. So basically, to summarize, if p squared is even, then it must follow that p is even. And we know that p squared is even, again, because p squared here is equal to 2 times an integer, right? And all even numbers are of the form 2 times an integer. But wait, I just said all even numbers are of the form 2 times an integer. So if p is even, then it must mean that we can write that p is equal to 2 times m for some integer m, right? But then this has consequences, because we can come back here, and since we have that p squared is equal to 2 times q squared, and we just said that p is equal to 2m, we can replace this p here with the form 2m and write that we have 2m squared is equal to 2 times q squared. But wait, 2m times 2m here is 4m squared. So we have 4m squared is equal to 2 times q squared. And then dividing both sides of this equation by 2, we can see that we can write that we can write that q squared is equal to 2 times m squared. And we said that m is an integer, right? And so what does that mean about q squared? Because then, since m is an integer, m squared is an integer, and this is of the form 2 times an integer. Well, you guessed it. This means that q is even, because q squared is even, and then that as a consequence means q is even, and this is a big fat contradiction, and this is the symbol for a contradiction. It's like, this is a big fat contradiction because we said that p over q was in most reduced form, and if p is even and q is even, then it couldn't have been in most reduced form, and therefore this assumption is false, and the square root of 2 is not a rational number, therefore it is an irrational number. Yeah? Alright, cool. This concludes the proof, and yeah, I hope you enjoyed it. Keep watching.